Hi guys, welcome to the third part of fluid statics video with me, Dr. Shida. So, on the previous video, we covered on the horizontal surface and then we went on to the vertical surface. Now, we want to know how to find hydrostatic forces for inclined surface. So, as you see in the diagram here, we have a surface which is submerged just below the water. So there is a distance between the top surface of water to your object. So how do we calculate this? So in order to do that, instead of calculating it because it is placed at an angle, we are going to transform this to horizontal. So we have the same surface but vertical. Okay, we are going to transform this into the y component. So now, how do we do this? So we know that b is the length, but now it is vertical, right? So we are going to change this to y and x components. So we have this angle here, so that is theta. So b theta is for x component will be b cos theta. For the y component, we will get b in terms of b sin theta. So that will be your height, your new height when we transform from inclined to vertical, b sin theta. Okay, and then we must not forget that there is a remaining height on top of it, so that is s. So s will be the same thing. We already have theta, so for x component is s sin theta, and for y component we have s I got that mixed up. It should be the other way around. So this will be s cos theta because the angle here, so adjacent to it, s cos theta, and then this one is s sin theta. Okay, s sin theta. Okay, so we got that now, and then we want to find this formula. In order to get this formula, or to get the hydrostatic forces, we know that for hydrostatic forces our formula is rho g h a. So our h here should be from the center of plate to the top surface of water. So that will include half of the distance b sin theta plus s sin theta, right? So here we'll get rho g, our h will be b sin theta over 2 plus sin theta times area. What is this area? So if we draw this, let's say this is the side view, our front view will look something like this. So this is our height, which is b, and then this is our width, so will be a. So it's a times b. So then you get rho g b over 2 plus s sin theta times a b, which is this formula. Okay, so we got that. So at this point, we already learned how to calculate the magnitude for hydrostatic forces for tilted plate, vertical plate, and horizontal plate. So we can use this formula which I've shown you before how to calculate those. And now we know that hydrostatic force is a force, alright? So when it's a force, it has both magnitude and direction. It's a vector. So magnitude we can calculate using this formula. But what about vector? How do we know where it is acting on the surface? So if you notice from this slide, we can see for each of these surfaces we have a YP. Okay, YP is the point of where the hydrostatic force is acting on the surface. So it should not be at the centroid, it is somewhere further below. So I will show you how to calculate this now. Okay, line of action for hydrostatic force. We know that pressure acts on the centroid of surface. So if we are calculating pressure of P, it should be acting at the centroid. If your surface is square, it should be half the height of the square. So that is YC, your length of centroid. It should be half of your surface. But however, for hydrostatic force Fr, it does not pass through the centroid. Okay? So pressure pass through the centroid YC. Hydrostatic force should be underneath where pressure is higher. Okay? So we are going to denote with YP. Gonna show you. Okay, so please notice, for hydrostatic force does not pass through centroid. Pressure pass through centroid. Okay, and then Fr will be underneath somewhere the pressure is higher. Okay, will be somewhere underneath the pressure. So we denote the length for centroid YC. We denote the line of action for hydrostatic force YP. Okay, so how do we calculate the length of YP? We can use this formula here. So to calculate line for the line of action for hydrostatic force or length YP, we use YC, the length of centroid, plus I of centroid, which is I is the moment of inertia of centroid, over length of centroid again times area of surface. Okay, so this is how it looks like. So we have our pressure acting on the centroid, and then we have our hydrostatic force acting somewhere below the where pressure is acting, which is slightly below. So we don't denote that by YP. So do not get confused by YC and YP. YC is the centroid of your object. Whatever your object shape will be, either it's circle, square, any shape. So your centroid will be different in these shapes. So depending on the shape, your moment of inertia will be different too. So that will affect your YP, okay, and YC. Okay, so this is how you calculate the moment of inertia. So this is the formula for I. Okay, if your object is your surface submerged underwater is square, so your area we will calculate it as A times B. A is the total length, Right? Let me change this to a thinner line. So this is your A. A times B, you will get the area, and the formula for moment of inertia for square object or rectangle is AB cubed over 12. So you will substitute that in your formula of YP equals to YC plus I, your moment of inertia, over YC times area. So if it's in this case, your area is AB, your YC will be the length of your surface. Your centroid will be somewhere here, so it will be YC. Okay, or this if the water is up until this point. If your water is somewhere higher, so your YC will be until the surface of water. Okay. Okay, so if your surface is circular, you will use this formula. So depending on the shapes that is given in the problems, you will use the suitable moment of inertia formula and area. Okay. Okay, now that we are done with our topic, which is to calculate the hydrostatic force as well as finding the line of action of your hydrostatic force, we will continue on doing some of examples in another video. Thank you.